Hi. So we are presenting our course project on unconditional room temperature quantum memory. We are reproducing simulations from the equations present in the paper of Nature Physics referenced here. They perform experiments on the same thing, but we are reproducing all of the data points as far as we could in simulations. So our group consists of Adi, Anuj, Sara, Soham, and myself. So the key goals of the paper are: first is unconditional storage. So after retrieving the data from the memory, we do not post select. We do not select the data points based on any noise measurements or anything. And then we want to beat the no cloning limit. So we need to achieve fidelity greater than 50%, which is the maximum limit in case of classical memories and classical storage of memories. And then we want to achieve scalability. So we operate at high temperatures without any cryogenics. The paper attempts the experiments at 80 degrees Celsius. However, this won't be included in our simulations. Next is the quantum motivation. Why do we need a quantum memory at all? The no cloning theorem states that we cannot measure an unknown quantum state without collapsing it. And because of the collapse of the measure, because the collapse of the quantum state, if we try to store a quantum state in a classical memory, the maximum fidelity which we can achieve is 0.5. The challenge is to prove our memory is quantum, and for this, the authors demonstrate a fidelity greater than 0.5 across all input states without post selection. And they go up to high mean photon numbers, even up to 1050, which will demonstrate it. Now, for this, they use a rubidium vapor cell as the memory device, which uses a lambda gem protocol. I'll explain the gem protocol next, but before that, a lambda type atomic system essentially means there are three states, which we can see in the figure here. In the figure A, the state 1 is the ground state, and the state 2 is the other state which will uh, include in the operation of our memory. And the third state is an excited state which acts as a bridge. But if it is largely tuned, then we won't have any noise source from it due to spontaneous emission. Now, this is called the effective two-level approximation, as we have written here. Now, the gradient echo memory protocol operates as such. First, we absorb. So each frequency component in the incoming data is stored at a unique Z position. For this, we create a magnetic field gradient within the memory cell, which I'll explain in the experimental apparatus. And this is then stored in the two-level system of state 1 and 2. And when the coupling beam is turned off, the coherent state is frozen in the ground states 1 and 2. Now we try to reverse the magnetic field, and because of this, we retrieve the memory back as an echo. This echo is an optical echo, since it would be again a light pulse going out of the memory cell. Now, to explain the experimental apparatus, this is a figure taken from the supplementary of the paper. First is the control field, which comes to the memory cell, and then there is a signal field, which comes to the memory cell. The signal field contains the quantum state which we want to store in the memory. Now, the magnetic coil, as you can see here, creates a linear magnetic gradient. And because of this, there is a linear gradient in the separation of the states 1 and 2, as shown in the figure B. So when we are shining a signal field on the memory cell, we have a certain gradient, because of which each frequency component of the signal field will be stored at a particular Z location, at which we have essentially the Rabi oscillations. So essentially, we have a resonance between the signal field frequency and the frequency separation between 1 and 2. Now, this will have an accumulated phase over the time when the data is stored in the memory cell, because of which we reverse the magnetic field gradient to neutralize this accumulated phase, and we retrieve an echo pulse out of the memory cell when we want to retrieve the data. This goes through a filtering cell and ultimately is detected using a homodyne detector, where we give an LO externally, which bypasses this entire experimental setup. And by the detection and by the two photodiodes D1 and D2, we measure the interference, and the difference current gives us the quadrature amplitudes X and P. Yes. So before we move ahead with Soham's explanation of the two-state evolution, I'll first explain the entire experimental setup. Initially, we create a weak signal field from a continuous wave laser using an acousto-optic modulator. It controls the exact timing and the shape of the pulse generated. We combine this with a control beam because the signal field is too weak to drive transitions inside the memory cell all by itself. Then within the memory cell or the rubidium vapor cell, we heat it to 80 degrees Celsius to achieve the necessary optical depth, which means that we control the transparency exactly as we want to. And then by the gradient echo memory scheme, we apply a linear magnetic gradient, as I explained, which is called eta. And this entire memory cell is isolated in a metal shielding. This is to eliminate any kind of background magnetic noise, ensuring only the gradient of the magnetic field of the magnetic coil is visible to the atoms within the memory cell. Next, to detect the quantum state retrieved from the memory cell, we used homodyne detection. And we do this 10,000 or 100,000 times as done in the paper for tomographic reconstruction of the original quantum state fed into the memory. This we in our simulations, we conduct the homodyne detection and the tomographic reconstruction of the quantum states both before the memory cell and after retrieving the data from the memory cell to show the comparison and calculate the fidelity. Even the authors in the paper do this experimentally. For the homodyne detection, as I said, we source a local oscillator beam from which bypasses the entire experimental setup of the memory, and we put it on a 50-50 beam splitter, where the retrieved echo meets the LO. And then we obviously use the two photodetectors, D1 and D2, to measure the interference, and from the difference current, calculate the quadrature amplitudes. Handing over to Soham.
Hi, so I am Soham. My role in the team was to produce and simulate the data points, the quadrature data points, which were act as a replacement for the experiment data. For that, we use a scheme. So experimentally, as we know that the memory cell is a long-lived hyperfine ground state of warm RP atoms. So because the paper uses experimental data, but we can't use experimental data. So what we do is we use a protocol called lambda gradient echo memory, which acts as a very efficient storage interaction sort of thing. Like this protocol is versatile for data manipulation and it provides a efficient storage without any memory contamination due to a field or something. And so it can replace the experimental setup and give us the data points needed for the reconstruction of this quadrature output. For that, we have a supplement in which we solve Maxwell block equations in a weak probe and off resonance regions. So we assume that we have a one photon detuning, a classical beam frequency, and a weak signal. The two photon detuning can be varied in time and made linear with a magnetic or electric field. And the delta T is given by eta times C. So we assume that all population is in state one. And we are in a, we then start that initial pumping is there. So to initiate the equation. So we effectively in lambda GEM, we have these three equations, but since we are considering we are in a very special case where we have weak probe and uh, far off resonance regions. So we can simplify these equations. Here the F's are the Langevin operators, which account for noise from spontaneous emission and ground state decoherence. But in some region, so in our region, we can ignore them because they are just adding an overall noise in the phase, and we can add the following noise numerically later. So we just ignore that and can be replaced by vacuum noise. And then we do a adiabatic elimination. So mainly our process is around the adiabaticity of the process. The lambda GM, effectively we uh, change the lambda GM to an effective two level model, and we saw equation of states for that, and we knew, and using those states we get E, and then we model quadrature values. So how do we do that is, uh, we can assume that the sigma 1 3 oscillations are smaller than the decoherence gamma, and we just drop that term, and the time scale of the system is very small than very greater than 1 by gamma, which is decoherence. We also assume that the one photon tuning is like really great number than compared to spontaneous emission rate. So by solving these Maxwell block equation in this field, we have effectively d is the 1 by dt is smaller than, very small than gamma, where d is the optical length, and the photon detuning effectively is greater than gamma d. And we need to ensure that this d is greater than the optical density, which is 1. So this is the collective thing, and we assume that the beam amplitude is real and photon detuning is 1. This is the transformation. So we effectively, uh, because of this level, we just tune it down, and we just are concerned about these two levels. So if you if you drop this term, put it 0, take its dominance. So it would be effectively minus gamma, since, sorry, not minus gamma, since we have delta very greater than gamma. We just drop these two terms, and we are left with minus iota. We are just concerned about the radial part, so we just drop the real part. And this can be obtained in terms of these three quantities. We just drop this, and we replace this part by this quantity, and this part by this quantity, and like in terms of this. And effectively, what we will get are these equations. So you can clearly see that with gamma delta, there is this sigma omega c square part, which is coming from the photon detuning, because we are just putting sigma 1 there. And this is the second part. And effectively, we get these equations. Now, we can always choose a frame where medium is normalized by refractive index. And we can choose coupling beam frequency to match the shift of this. So effectively, we can, in such a frame, in the light where it gets normalized by the refractive index and this guy. So we can just drop this term, and this guy gets normalized by coupling frequency. So we get effective two system, this, which we need to solve. So here G prime is just G sigma omega C by delta, and N prime is N omega C by delta. So numerically, we are left with solving this equation. And yeah, so that is the part where we get, so after numerically solving this, we will get sigma and E. Now we are concerned with the E value, which we will further use to generate quadratures uh, using multi-mode thermodynamics reconstruction. So let's move to the actual code. So yeah, I explained you with the help of paper that this is the process we are going. These are the equations which effectively come down to these two. So I also tried to solve it in Fourier domain. So I just took a Fourier transform and converted it to these two equations. I was trying whether this can be solved analytically or not. But turns out that this is also analytically complex because you have a delta of, so you have this term, then you have this term as well, where sigma is just sigma tilde. So we have this term, and then this, yep. So these are computationally more complex than this pair of equations. So I just use them to solve it numerically. So I just define a grid with dc, dt, c is like the length, L is the length of the memory box over which we are evolving this system. Time is the total time. And then we define our input pulse, which is, we assume that the input pulse is basically a Gaussian pulse with mean value 2 and the width is around 0.5. And then we define the matrices, like initialize the equation, solve it using RK4. And yeah, that is still this. So we essentially get E out value after solving the whole this equation system. Now, further to develop the quadrature values, what we do is that we map the field, like the E, to using a temporal mode integration. The input and output fields are projected into envelopes using a base function, which is a mode function, sorry, which is essentially a Gaussian pulse. And what happens in this process is that during evolution, as the pulse crosses the half of the time, we switch the gradient field using magnetic field to recreate the memory. So say like for the first half of the time, we have positive gradient for the uh, delta, the control field. And for the next, like for the detuning, we have like positive gradient first half in the first half, and we have a negative gradient during the second half. So it effectively tries to recreate like the original signal we had. So we need to do a time reversal in this mode function to get the E out. E in, we use just the simple Gaussian mode function. For E out, we just use a exact copy of it, but with a time reversal. So here, as you can see, I define an input Gaussian UE, normalize it. Same Q out I define, but I do a time reversal and then normalize it, and then I calculate the alphas. And then to calculate quadrature values, we need a mean photon number. Since we are using coherent pulses, the photon number is just like the alpha, mod alpha would be just square root n bar. So we just multiply we just generate quadrature, which would be given by, also the paper uses convention for quadrature as A plus A dagger. So we are also using that. Then for quadrature value using a local like, so in the homodyne calculation, we will have a local oscillator with varying phase. So we incorporate that and we get x theta as 2 real part of alpha e iota theta, where theta is the local oscillator phase. Plus we add a vacuum noise as we had dropped the Langevin operators. So we add a vacuum noise to accommodate that. And that was also a normalized, like using a a normal distribution. And then uh, so we have like we have these parameters G and gamma eta, which are the gradient, which are not specified in the paper. But we know that these parameters should be such that the value of G prime times N prime times divided by gamma should be greater than unity, which is true because it's around 20 and it satisfies the whole memory business, the adiabatic approximation. So yeah, so we do that. And yeah, this is so also this is done, the allo phase shift, to ensure that the paper fixes the value of, as you can see in the main paper, that they fix got value 0 at minus, so the value fixed value minus pi, 0 at minus pi, and like maximum value at minus pi by 2. So we also use the same convention and fix, just add a global phase shift. So you doing that, variance for then vacuum would be 1 in this condition, and then we just evaluate over n bar. So here I am scaling with n bar, and yeah, that is sort of graph we are getting. And this is the actual experimental graph they have plotted. So it kinds of agrees around in some efficiency value. So we haven't multiplied efficiencies and all, we are considering a very ideal case. So this is how homodynamic structure is being reproduced here. This is the whole argument behind it, that we have a memory system to evolve with. We take E, you generate quadrature values. You will have like input quadrature and a output quadrature, because you have a E in, E out, and you have two modes. And then you basically couple it with a local oscillator phase, and effectively you get this sort of distribution, fixing at minus pi by 2 as maximum. So yeah, that was from my side.
Hello,
Uh,
my name is Adi Bharatiya, and I will be explaining the next part of the code, which is the reconstruction of the density matrix, as is given in the paper as well. So you can see that the figures here are from the homodyne measurement, which was simulated in the previous part of the code. And now we want to know how we got these density matrices for the input state and output state respectively. So the input is on the left, the output is on the right. So how do we do this? So let's start from the beginning. Right. So the grand goal, of course, as we know, is to determine the quantum state of the light, which was stored in our quantum memory. And we also want to compare it with the state that we sent in. Now, classically, as we know, everything can be measured directly. But in quantum mechanics, of course, we cannot observe the full state. So instead, we measure different outcomes and we try to reconstruct the state, which is called tomography. And the quantity of our interest in this case is the density matrix rho. So what exactly is a density matrix? Now, if I put it very simply, it is a representation of our knowledge or lack of knowledge of a certain quantum state. So it represents a probabilistic mixture of states, and it also takes into account the probabilities of those states. So, for example, here I have written a general quantum state, rho equals sum over m comma n, rho mn, ket m bra n. So this is in the fork basis, since m and n are fork basis states. And now the diagonal elements of this matrix, rho nn, they represent the probability of having n photons. But the off-diagonal elements, n not equal to m, they describe the quantum coherence. So overall, the goal here is to find all rho nn. Now, moving back to the homodyne measurement, we started from this particular observable, x theta, which is a e to the power minus I theta plus a dagger e to the power I theta. So a and a dagger here are, of course, the annihilation and creation operators. And theta is the phase of the local oscillator, which we control experimentally. Now, every measurement of this operator is going to give us some real quantity, small x. So we propose the following process now. So we create bins in the phase space, So for every theta I on minus pi to pi, for every theta measurement, we also create multiple interval bins in the quadrature space. So through several measurements, we measure the counts in each of these bins for every theta I. So essentially, we are trying to create a histogram that will give us an experimental discrete probability distribution, Px x given theta. I will also elaborate on this further. But each homodyne measurement, as we know, corresponds to this particular measurement operator, pi of theta given by ket x theta bra x theta. Now, what is x theta? X theta is just the eigenstate of the capital X theta operator. So I want to now relate x theta to x at theta equal to 0. And this relation is given by the unitary operator e to the power iota theta a dagger a. And x is just the eigenstate for theta equal to 0. So in the Fock basis, if I expand this x, I will get these coefficients psi n of x for different n. And these are well-known functions. So these are called the Hermite-Gaussian functions. Now that I know the relation between x theta and x, I can also expand x theta in the Fock basis. And when I do that, I'm just going to get an additional factor of e to the power minus in theta over here. So as I said, psi n of x is the nth Hermite-Gaussian function. Now I'm going to try to build my projection operator in the Fock basis from all of this. So finally, I get pi of x comma theta to be this double summation over n comma m. So these are the Hermite-Gaussian functions, and there is an exponential of iota m minus n theta. Now, the probability distribution that we actually got is related to the density matrix through the following equation. This is one of the properties of the density matrix. So P of x given theta is given by the trace of rho times pi of x comma theta. And now I can express this in terms of the matrix elements of rho in the Fock basis. So now you can see that P of x given theta is related to rho nm. Now I want to finally come to the main algorithm that has been used, which is the MLE algorithm, maximum likelihood estimate algorithm. So we again start with the bins that we had created in the phase space and quadrature space. So let theta j, for example, denote the phase bins and xk denote the quadrature bins. Then capital Njk is just the number of counts that we got from the homodyne measurement in bin xk comma theta j. So now, according to this, we can calculate the experimental probability as follows. So Px of xk given theta j is just njk, and in the denominator, we will sum over all k's because we are summing in the quadrature space. So summation over k of njk. And what will this be theoretically? This was, of course, what we got experimentally. But theoretically, as we said earlier, it is just the trace of rho times pi jk. Now pi jk is xk comma ket xk comma theta j bra xk comma theta j. Very similar to what we did earlier. So I've just replaced x theta by xk comma theta j since it is discretized now. And my likelihood function, therefore, assuming independent measurements, is just going to be product over all j comma k, p theoretical, xk given theta j, whole to the power number of counts, njk. So this pi here is not the projector. This is a product over all j and k. Now I take log on both sides as is commonly done in the MLE method. So I will get log L. And now you can see that log L is directly dependent on the parameter in this case, which is rho. And of course, the following constraints have to be enforced on rho. So rho has to be positive definite, and the trace of rho has to be 1. Now, trace of rho being 1 turns this problem into a variational problem. So essentially, we want to maximize this quantity, which is log L rho minus lambda times trace rho minus 1. So in order to maximize the above, we now employ this iterative algorithm. So I'll walk you through the steps. So step 1 is, of course, initialization. This is the initial guess for rho, which is simply identity n cross n over n, because we want the trace to be 1. And n is just the cutoff for the number of Fox states that we are taking in our Hilbert space. So here in our code, it is 20. The next step is, of course, to compute the probabilities pjk, which, as mentioned before, is trace of rho times pi jk. Next, we introduce this matrix R, and R is defined as shown here. So summation over j comma k, njk is of course the number of counts, over this computed probability pjk times pi jk. And then finally, the last step is to update rho. So rho has to be updated according to this equation. So R rho R over trace of R rho R. We are dividing by the trace in order to normalize rho, in order to ensure that the trace of rho always remains 1. So I hope that explained the code well. This is exactly what the code is doing. And coming back to the figures, here you can see that these are the input and output matrices, and they look very similar, which is a good sign. Yeah, that's it from my side. Thank you.
Hello everyone, my name is Anush, and I will be explaining the next part of the paper, and this covers photon number distribution and the Wigner function representation. So in quantum optics, the photon number distribution basically describes the probability of finding n photons in a given quantum state. And it is defined as the nth diagonal element, matrix element of the density matrix of our state. So here rho is the density matrix and n's are the Fock states or number states. For a coherent state, the photon number distribution follows a Poisson distribution. So probability of finding n photons in our state is given by lambda raised to n e raised to minus lambda upon n factorial. Here lambda, which is equal to mod of alpha square, is the mean number of photons in the state. And for such a coherent state, the mean and variance in the number of photons are both equal to mod of alpha square. And a coherent state represents classical like light. So it is the closest possible state to a classical state. And it has no excess noise beyond quantum fluctuations. In our experiment, the input states are nearly coherent. So the measured distributions are expected to follow Poissonian statistics. Now coming to the effect of quantum memory on photon statistics. An ideal quantum memory should preserve the photon statistics and not introduce any additional noise. However, real systems may introduce Gaussian noise in the quadratures, and they may also not be fully efficient. So there can be a loss in the number of photons. And as you can see from the supplementary material of the paper, the memory is modeled as adding equal noise to both quadratures. And the noise added is, of course, Gaussian. And this noise modifies the reconstructed photon distribution. Now, how is the photon number distribution actually obtained? Now, this is not something we can measure directly. Instead, the process involves performing homodyne measurement of quadratures, and reconstructing the density matrix using maximum likelihood estimates. And using this reconstructed density matrix, we extract the diagonal elements, and using that, we basically construct the probability distribution. All of this has been explained in detail in the previous section. So coming to our code. First, we define a function called Poisson, which takes in two parameters n and lambda, and it returns the Poissonian probability. Now in the next part, n distance is an array which contains the diagonal entries of our initial density matrix, and n values is simply an array of the length n distance. This is basically our photon number axis for the plot. Now the next part of the code involves fitting a Poisson distribution curve, a smooth curve, onto our given data, and using this we will find the mean lambda, which is the most likely lambda, which perfectly fits our given data. We do the same for the final density matrix and find the mean lambda in the final fitted curve as well, and then we compare both curves. So as you can see, for our data collected, this is how the input and output photon number distributions look like. Now, clearly, they are both Poissonian in nature, which means they represent coherent states, nearly coherent states. And the lambdas are also nearly the same. The slight difference occurs because of the efficiency factor which we introduced in our earlier code. Now coming to the Wigner function representation. The Wigner function provides a phase space representation of a quantum state, and it is analogous to probability distribution in classical mechanics. In fact, it is defined as a quasi-probability distribution over the amplitude and phase quadratures. Now, why quasi-probability? Because unlike classical probability distributions, it can take negative values as well. And these negative values are signatures of non-classical phenomena. So it gives us an intuitive picture of a quantum state in phase space. Now for a given density matrix rho, this is how the Wigner function is defined. Now, although the Wigner function is also not directly measurable, it can be constructed via homodyne detection of the quadratures, which is what we do in this code as well. The Wigner function can also correctly produce measurable distributions. So integrating out one of the quadratures gives us the probability distribution of the other quadratures. And for a coherent state, the Wigner distribution is Gaussian in nature, which is what we observe in our plots as well. So coming to the code, this part of the code basically constructs the Wigner function using the initial and final density matrices and plots them. So as you can see from both of these plots, the Wigner function is a Gaussian. It is concentrated towards the center, and then as you go far away from it, it dies out. And it is nearly the same, which is what we expect in our setup.
Hello, my name is Sarah, and I'm going to talk about the figure 4 of this paper, which basically contains the following two things, the fidelity and the TV diagram. And before we get into this, I'd like to start off by talking a bit about the quantum memory and what the loop learning theorem means. So, a quantum memory is basically any device that maps the quantum state of light into a long-lived matter excitation and which basically later retrieves it. Now, in a continuous variable system, the state of any light is given by two quadratures, the amplitude and the phase, which are the x quadrature and the p quadratures respectively. Now, the no-cloning theorem is one of the benchmarks in quantum, and it states that any arbitrary quantum system cannot be perfectly copied. Now, here's a small proof of how it's done. Now, let's take a unitary U, and it's acting on the states psi and 0, and such that it takes this the state psi 0 to psi. Now, for another state, phi 0, the same unitary takes it to say phi. Now, taking the inner product, you get the fact that the inner product of psi and phi is equal to the square of the inner product of psi and phi, which basically implies that the inner product of psi and phi could either be 0 or 1, which says that perfect cloning is possible only if the states are either um, orthogonal or if they have complete overlapping. That is, if the inner product is either 0 or 1. For any other possible overlap, the perfect cloning is impossible. Now, in the context of quantum memory, what happens is the device is attempting to store a state that cannot produce an output with that is a perfect replica while simulating or retaining a perfect copy within the memory. More importantly, it cannot like a memory cannot be a function by measuring the input state to extract its classical parameters and re-prepare it. So the measure and prepare strategy is basically limited by the Heisenberg uncertainty fields. So then what happens is um, the act of basically measuring one quadrature that induces some kind of noise into the opposite or the conjugate quadrature. That is, if I want to measure the quadrature x, it is going to impose some noise into quadrature p. And now we want to basically find out the trade-off between those between measuring these two quadratures, such that we could get the optimal result. Now, how we do this? First, let's come upon the first parameter, the fidelity. So the fidelity is basically the overlap between the input and the output Gaussian states, that is psi in and psi out, where psi out is basically the retrieved state, and psi in is the input quantum state. That's it. Now, the fidelity is given for Gaussian quadrature or for Gaussian states. The fidelity is given by this big expression that you can see here. And there are two major limits that are imposed in while calculating or measuring the fidelity. One is the classical limit, which is basically uh, it's a maximum fidelity that you could achieve by any scheme that, say, performs independent measurement of the conjugate observables, X and P. So, if you're basically independently measuring these quadratures or the observables, and then you're re-preparing the states based on those measurements, maximum fidelity that you could get is limited by this classical limit, which is 0.5. And there's another limit, which is called the no cloning limit, which is a more stringent bound, so as to say. And it's basically a proper, it gives a proper measure that if I have a fidelity above 0.68, it ensures that the memory is not just a mere clone, but it's preserving the unique identity of the input state. So it's uh, it's basically a, it tells you that the measurement or the memory is purely quantum. Now, um, The fidelity is basically it's state dependent because for say pulses with like say low photon number, the impact and efficiency of fidelity is say for example less pronounced than say any high amplitude pulses because the vacuum state is said to be a fixed point for a loss. However, at low photon numbers, the fidelity is extremely sensitive to added noise. And that makes it an excellent probe for memory contamination, basically. Now, coming upon to the next theory that we want to get into further, the TV diagram. It's basically another trade-off measuring diagram, so as to say, between the two parameters, the signal transfer, which is T, and the conditional variance, which is given by V. Now, what happens is the T plus and T minus are basically the signal transfer coefficients, and they measure how well the signal to noise ratio or the SNR is preserved throughout the memory for each quadrature. So it's just basically defined as SNR, the fraction of SNR of the output as compared to the SNR of the input for both the quadratures. And it is given by theta divided by 1 plus V out minus Vn for each of the respective quadratures plus or minus given whatever. And just for the sake of completeness, let me just add one more thing that if I have a noiseless, perfect memory, perfect preservation of memory basically, my T plus and T minus both should be equal to 1. But in classical measure, the maximum sum of the possible two transfer coefficients is equal to 1. Now, coming upon the next parameter that we have, it's the conditional variance. The conditional variance is basically like a quantification. It basically is like that's the measure you use to quantify the noise which is being added to the signal. And you need the knowledge of the input state to measure the conditional variance. Now, uh, it's given by this this formula right here, and this for purely Gaussian systems, this further reduces to VCV is equal to 1 minus T, where T was the signal transfer coefficient times V out. Now again, for a noiseless memory, VCV is going to be 0, as we can see it clearly. And for the classical way that we used to do it, which is basically you initially measure the quadratures independently and then you prepare the scheme, VCV is going to be 1 for each of the quadratures. Now, the no cloning criteria. You know that a quantum memory is surpassing the no cloning limit, which for the fidelity was 0.68. Now, you know this is like you know what the memory is quantum when the information transfer, which is T plus plus T minus, is greater or equal to 1. And the quantum correlation, which is basically uh, VCV positive times VCV negative, is less than 1. So that gives us a good enough, like a beautiful block to work upon. To see if the memory that we have got, if it is completely quantum or if it is quasi-quantum or quasi-classical. So now that we are done with the theory of these two plots that we are going to do, let's get to the code to briefly talk about what it does. Initially, we define these three functions: get quadratures, loss variance, and compute TV. So get quadrature is basically like in homodyne detection, the local oscillator has a particular phase. And now what we do in this we scan the phase to obtain the particular quadratures. So at phase theta equals 0, we get the quadrature with we get the amplitude x, and for theta equals pi by 2, we get the quadrature p or the phase. So we are and to ensure that the data that we have is correct, we make or we select those quadratures appropriately. You're basically what you're doing is you're putting a phase mask with for all your data that you have and selecting the particular values of data depending on the values of theta, which is basically the phase of the local oscillator. Now, the loss variance is just like so, as we talked about earlier, that we have to find out the true performance of the memory. We need to account for all the losses, basically, and the external detection losses, which could include like detector efficiency or homodyne visibility or filter attenuation as well. Um, so we basically what it was, if we correct it is basically we measured minus one divided by eta of detection plus one. So that's just how we calculate the corrected variance, so as to say, which takes into account the noise or removes it. Nothing. And this third is basically just computing TV using the previous formulas that we discussed earlier. Now, here what we do is um, we are kind of reconstructing the quantum state and the fidelity. So, as my teammates had previously talked about, and uh, in the previous sections about the reconstruction of the MLE. So, because like a single homodyne is a measurement gives you like one slice of the data, so as to say. This code uses a maximum likelihood estimator to find out the density matrix P and like the most likely produced whatever the observed distribution is. And so initially you're taking a set of values of n bar, which is a mean photon number, and working out for each of them with a constant eta. Eta was uh, as we defined earlier, and as we need for each of those values of mean photon numbers, we need to change the Hilbert space or the size of the Hilbert space, sorry. And so I'm changing that dynamically with the photon number n bar. And yeah, uh, given that, and then we calculate the fidelity using the Q-tip function, which is the square of trace of under root rho L times rho out times under root rho L. Yeah, the formula that we spoke about earlier. And yeah, and this is basically you're just plotting these two functions. And here are these results of fidelity. So in here, what happens is, as you can see, the fidelity reduces with the photon number. And the maximum that I have went up to is 22 point something. It must be somewhere up there. But yeah, and this two is the classical fidelity limit that we spoke about earlier, which is 0.5. And this is the no cloning fidelity limit, which is 0.68. And we can see that all of our measurements or all of our fidelity values are above this no cloning limit, which is a guarantee kind of, so as to say, that our memory is completely quantum. And this is the TV diagram wherein uh, the fourth quadrant over here, this gives you the no cloning region, wherein T is greater than so this must be and yeah, it's one. So yeah, so T plus T minus should be greater than one, and the product of v plus and v minus should be less than 1. And this is almost on the edge of the no-Knowing region, but yeah. So these were this was basically the analysis of our memory and how well our memory performs as compared to the actual limits of no-Knowing theorem. And so uh, this basically concludes our entire project, which was about quantum memory. And this paper particularly demonstrates how like the fundamental principles of quantum mechanics can directly constrain the performance of quantum memories. And this was one of the proposed ways to um, basically store the given state of light. And yeah, thank you.